Hey guys, this is Fozon, and in today's lesson we're going to be doing an introduction to recursion. Our lesson objectives, we're going to learn what recursive methods are and interpret them. We're also going to learn the general form of recursive method and how to code them through a factorial algorithm. So what are recursive methods? Recursive methods are just methods that call on themselves, meaning that there is a method the method invokes itself within the method. Generally, there will be a base case, and what this base case does is that it prevents the method from calling itself. However, when you're accessing these recursive methods, there will generally be one recursive call, at least one recursive call. Whenever a method calls on itself, it has its own set of local variables, so remember to keep scope in mind when you're interpreting recursive methods. Within the general form of a recursive method, there are two cases, the base case and the recursive case. The base case, as I said, is the method where it causes the method is the case that prevents the method from using recursion, meaning that it causes the method to terminate eventually. Without it, the recursive method will continue calling itself, and that's not really practical for our algorithm. The recursive case utilizes recursion, and that is the case that leads to the base case. It calls on itself until it can no longer call on itself because it has reached the base case. So the general form is best illustrated through a recursive problem. What does the method return when computation for is called? Computation is the name of the method, and for is the argument that we're inserting into the method. As you can see, we have both our base case and our recursive case both easily displayed. We could tell that this is the base case because it doesn't utilize recursion, the if statement, and within the if statement it has no call to the method itself. Within the else statement, however, this is our recursive case, because although it does have an integer or does return an integer, it returns an integer as well as a multiplied by a call to the method itself. So it's utilizing recursion to call on itself. So let's interpret this method. So if we put for into this method, it's not going to execute this return statement because for is not equal to 0. This would be a false statement. So it would go immediately to the else statement. And it's going to be like 2 times computation j minus 1. Well, j was equal to 4, so it's going to be 2 times computation 3. So computation 4 is what we ultimately want to get. But to get computation 4, we need to do computation 3 and then multiply that by 2. So let's do computation 3. We plug in computation 3, and we find out that 3 is not equal to 0. So we go to the recursive case, and the recursive case states that to get computation 3, you have to do 2 times computation 2. Okay, so now we need to know what computation 2 is. Let's plug in 2 into our method. 2 is not equal to 0, meaning that our base case is not fulfilled. We go on to the recursive case, and we find out that computation 2 is equal to 2 times computation 1. Okay, we need to find out what computation 1 is. So what is computation 1? Well, we go back to the if statement, but we have 1 as our argument. So is 1 equal to 0? No, it's not. So we go to the recursive case, and we find out that computation 1 is equal to 2 times computation 0. So we go back into the method, and we're like, okay, integer j is equal to 0 now. Now our base case is fulfilled. This prevents the method from calling on itself so many more times. As you can see, we already called on the method itself 4 times, and we don't want to do it so many times, or our algorithm should be designed not to do it till infinity. We have to have an end to our recursive calls. So when it finally reaches computation 0, we've reached our base case because the argument is 0. And if j is equal to 0, it should return 1. So if computation 0 is now 1, then we know that computation 1 is equal to 2 times 1. 2 times 1 is equal to 2. So now we know that computation 1 is equal to 2. Let's plug computation 1 into our computation 2 calculation. Computation 2 is equal to 2 times computation 1. Computation 1 is equal to 2, so 2 times 2 is equal to 4. 2 times 4 is equal to 8. And then 2 times 8 is equal to 16. Through this algorithm, we've pretty much found out that computation 4 is equal to 2 times computation 3, and computation 3, as we said before, is 8. So 8 times 2 is 16. So our final answer when we call on the computation method with the arguments 4, integer 4, should return 16. Before we construct a factorial algorithm that utilizes recursion, let's first actually find out how we can construct it through learning factorials. So if you haven't taken a math class, or you haven't really been adjusted or learned about factorials, let me explain it to you. So factorials are basically just a way of multiplying the number against all the numbers that come before it. So if you look at 5 factorial, the exclamation point tells us that we want to get a factorial. We simply do 5 times 4 times 3 times 2 times 1. To get 4 factorial, we do 4 times 3 times 2 times 1. For 3 factorial, we do 3 times 2 times 1, 2 factorial, 2 times 1, and then 1 factorial and 0 factorial, which I will discuss a little bit later. But if you notice the pattern from 2 to 5 and any number that's greater than 2 or greater or equal to 2, you notice that it's basically just the number that we're currently on times the factorial of the previous number. So technically speaking, you can rewrite 2 times 1 as 2 times 1 factorial. You could write 3 factorial as 3 times 2 factorial. You can write 4 factorial as 4 times 3 factorial. And you can write 5 factorial as 5 times 4 factorial. This is important in interpreting how we can construct our factorial algorithm. Now let's look at 0 and 1 factorial. Well, 1 factorial is interesting because it technically includes the 0 factorial. And you can actually put the 0 factorial as a part of every single factorial. However, we generally leave it out because it's a little bit misleading. Because, when you look at 0 factorial, it doesn't look like it can be 1, but it is. And some math teachers will derive it for you. However, I'm not going to do that. But just for the sake of knowing this, 0 factorial is ultimately 1. But it doesn't have any factorial behind it. So we can use 0 factorial as the base case. And then any number that's greater than 0, we could do a recursive call to the previous factorial. So we can write it as 1. If we're doing a call to 1, then we could do 1 times 0 factorial. If we're doing a call to 2, we could do 2 times 1 factorial. If we're doing 3, we could do a call 3 times 2 factorial. So basically, to illustrate factorials, it's basically n times n minus 1 factorial. That is basically our recursive call. N is the number that we're currently at, or the number that we want to get a factorial of. And then n minus 1 factorial is the recursive call. So let's implement that into our algorithm. I'm in the compiler, and I've avoided the hassle of making a main method by doing it outside of, the video. But just so you know, we have a scanner declared, and it just simply asks the user what number do you want to find the factorial of. So if I want to find the factorial of 2, it will return me 2. And you could do this for whatever number until you do any number that is less than -1. Anyway, the goal is to make the implementation for the factorial method. And to prevent any errors, I've already put a -1 return type, although that's what we're going to change within our video. So first things first, I want to make a base case. So if the base case is 0, that means that when the argument is 0, we get an integer I argument that is equal to 0, then we want to return 1. Let me go back to our presentation. So the base case is 0, and we want, the base case or the base argument is 0, and it should return 1 because 0 factorial is 1. So let's do that. If I is equal to 0, let's return 1. And I'm going to label this, that deleted it. Let me label this the base case. Now let me make an else statement. Now within this else statement, what I'm going to do is make the recursive case. And as you can see, the recursive case is n times n minus 1 factorial. So the n is the number that we're currently at, assuming that it's not the base case being 4. And then n minus 1 is the call to the factorial method. So let's do that. So else we do return, and since I is our argument, actually let me change it so it makes more sense with the PowerPoint that I have up. So we have n, for example, here. So I'm going to take an integer n. If n is equal to 0, we're simply going to return 1. However, if it's not equal to 0, well, let's do n times, and then we call the factorial method. And to ensure that we're not putting the same number within the factorial method, we do n minus 1. This will allow it to approach the base case because we have any positive number. That's the precondition, by the way. Precondition, any positive number. Or let me be even more specific. Any positive integer argument. And it will make a call to that method, n times factorial n minus 1. And the reason why we have n minus 1, again, allows us to approach the base case. Let's see if this works. So enter a number. Let me fix that. Enter a number. Okay. Enter a number to find the factorial of, or enter -1 to quit. So let me enter 2. And we get the factorial of 2 is 2. Let me try 3, and that should hopefully return 6. Factorial of 3 is 6. Let's do 4. That should return us 24. Again, you could look at this chart as a reference. And then finally, let's see 5. Good. And just to make sure that our base case works, let me ask for the 0 factorial. And as you can see, it returns factorial of 0 is 1. It doesn't even make a recursive call. Let me edit this method so that we can remove the else statement. So let me do that. Actually, let me first quit so that it doesn't run. Okay. So within an if statement, if you have only one line, you can actually remove the curly brackets, because if it's one line, then you don't have to worry about it interpreting anything else. So I can actually remove this. And since we don't have an else statement, we can simply remove the else. Since we don't have an if statement, we can return the else statement. Now you're probably wondering, why do we have two return statements one after the other? Well, we know that this will only execute if the if statement is true. And if the return statement gets executed, it doesn't even look at anything after that return statement. So if this is true, then it will execute and won't even look at the recursive case. However, if this is false, then it will look at the return type here. Let's test this out. 0 is 1. 1 is the factorial of 1 is 1. Factorial of 2 is 2. Factorial of 3 is 6. Factorial of 4 is 24. And factorial of 5 is 120. And we could even stretch it. Factorial of 6, I don't know what it is. Oh wait, it's 720. So this wraps up my video on the introduction to recursion. There's so much that you could do with recursion, but it requires algorithmic thinking and keeping in mind what your value is equal to at every single method call. So remember to keep that in mind. Remember to keep track of the numbers and the local variables at each method call. And that is ultimately the key to understanding recursion. Thank you for watching.